We have been looking at equilibrium conditions under static positions of bodies. We now wish to apply this to a particular structure called truss. These are structures that are used to distribute loads, and you have seen them when you travel. For example, across a bridge you see a structure like this, and here is the road. This structure helps to distribute whatever load there is on the road and takes it to the sides here. This is known as a truss, and in this lecture we wish to analyze the trusses using equilibrium of forces that we have learnt earlier. Another example of truss that you see around is the pillars that carry electric wires that have this kind of structure, and the wires are going like this. These are also trusses. In this case, the structure is essentially a two-dimensional structure. So, these are known as plane trusses, and these are three-dimensional trusses. In this lecture, we will be focusing on plane trusses. Before we start on trusses, I would like to remind you of certain things using the force and torque balance conditions that we have learnt earlier. So, let us see what happens when there are only two or three forces acting on a system. Number one, I am going to look at if there are only two forces. If a body is in equilibrium under two forces F1 and F2, then for body to be in equilibrium, the forces must be collinear and opposite, so that F1 plus F2 is equal to 0. If they are collinear, then about any point the torque also vanishes if they are equal. So, this is the condition for equilibrium. Next, if there are three forces, in that case the forces should either meet at a particular point, so that F1 plus F2 plus F3 not only is 0, the torque due to three forces is also 0. Another way they can provide equilibrium to a body is if they are parallel. So, two forces could act in this direction and the third force could act opposite. In that case, about any point, about this point for example, the torques would be in opposite directions due to F1 and F2, and they will balance out. This is something we are going to use later. Next, a very important thing let me talk about is static indeterminacy. If there is a structure or a body and it is in equilibrium under certain forces and constraints which are holding it together, then if the number of constraints are more than required for it to be for more than minimum required for it to be in equilibrium, then the system is known as statically indeterminate. If the number of forces, number of constraints are just the number that is required to keep it in equilibrium, then the system is statically determinate. In the case of statically indeterminate systems, the extra constraints that we put, which may be removed without disturbing the equilibrium, is known as the degree of indeterminacy. This is all illustrated very well with an example. Let us take a rod which has a pin joint at the lower end, and let us say it has weight W. For it to be in equilibrium under this weight, it will have to be supported on this side by, say, a wall, and that is enough to ensure equilibrium, because in this case, if I look at the free body diagram of the rod, it will have a force acting down, which is its weight. There is a reaction in the y direction due to the pin, one in the x direction due to the pin, and there is normal reaction on the wall. These forces are sufficient to bring this rod in equilibrium. Let us see how. So, I have this rod with a pin joint here and a wall here. This has a force R y, R x, a normal reaction due to the wall, and its weight. The equilibrium condition summation f x equal to 0 gives R x equals n. Summation f y equal to 0 gives R y equals to W. Now, about this point, the lower point, let us say the spin joint is O, the torque also must be balanced. If this angle is theta, the length is L, then we have summation torque about O is equal to 0 gives W times L over 2 cosine theta is equal to n times L sin theta, or n equals W cotangent theta divided by 2. Notice that in this problem I have three unknowns, n, R x and R y, and precisely three equations 1, 2 and 3. So, I can determine each and every unknown exactly. This problem is statically determinate. Let us look at indeterminate, corresponding indeterminate problem. If I take the same rod and put a pin joint here and also a pin joint here, in that case this is the weight W. I will have R y 1 and R y R x 1 on the lower pin joint, R x 2 and R y 2 on the upper pin joint. In that case, you see that number of unknowns are 4, R x 2, R y 2, R y 1 and R x 1, and number of equations are still 3, summation f x equals 0, summation f y equal to 0, and summation tau about any point is 0. So, I am putting an extra constraint here by providing a vertical force at the upper pin also. The conditions I get are that R x 1 is equal to R x 2 according to the way we have shown directions, R y 1 plus R y 2 equals the weight, and third condition is the torque condition. You see, all I can determine through this is r y 1 plus r y 2, not r y 1 and r y 2 individually, and this is the degree of indeterminacy. So, this is statically indeterminate problem and degree of indeterminacy is 1, because I can remove this constraint of providing a vertical force and still keep the system in equilibrium. Now, to motivate the trusses, I note 2 points. Number 1, for any point object to be in equilibrium, in general there should be 3 forces acting on it, minimum of 3 forces. And therefore, if I want to make a structure where each joint is in equilibrium, I should provide 3 forces there. There could be 1 external and 2 by something else, or 3 members extending applying forces. For example, let us take a structure where I take a rod and make a pin joint at one end of it, and suppose I want to load it at a particular point. Let me first make a structure of 3, taking 3 rods and provide a pin joint at the circles. Now, you see, this pin joint has 3 forces acting on it, 1 by this member, 1 by this member, and 1 external force. So, this can be in equilibrium. However, this joint and this joint are not acted upon by 3 forces, and therefore, to make the structure, make these points come under equilibrium, I have to provide more forces. I could do that by providing one more rod here, which provides 3 joints to this, 3 members, 3 forces to this point, and then make one rod here, so that this point is also under 3 forces, and make a joint here. However, the moment I do that, this joint is only under 2 forces. I have 2 choices, either provide a full support here, or another choice, and I will make it in a simple manner now, 1 joint here, 1 joint here, 1 joint here. This is a fixed joint. Here I earlier provided a joint, a fixed joint, but now I will put another rod here, another member, and make a fixed joint here. However, the moment I do that, this joint will not be in equilibrium, because this is acted upon only by 2 forces, one by this fixed joint and other by this rod. So, I have to provide one more member to bring this point into equilibrium. The moment I do that, I have one free end of this member here, which also has to be brought into equilibrium. I could provide one rod this way and one rod this way, and this entire structure would be capable of remaining in equilibrium. This is a truss, a plain truss. So is this. So, you see, if I keep making structures like these, I would provide at each point enough forces to keep that point in equilibrium. If I load this structure somewhere, I could load it with some weight here, I could load it here. Each point is now can be brought into equilibrium by forces generated in these members. These members would provide just the sufficient forces to bring this entire structure into equilibrium, and in the process transfer this load onto the fixed supports. This is the job of a truss. If you analyze it carefully, you will see that the number of members that I need to do this is equal to, let me write the number of members equal to m is equal to 2 j minus 3. In this case, I provide just enough constraints in the system to make the system statically determinate. If m is larger than 2j minus 3, where j is the number of joints and m is the number of members. Let me write it here. M is equal to number of these rods, let us say, and j is number of joints, then the system becomes statically indeterminate. I have provided more constraints than are needed. If on the other hand, so this is statically indeterminate. On the other hand, if m is less than 2j minus 3, then the system is unstable. I have not provided enough constraints or enough members or rods to provide enough forces to keep the system in equilibrium, and therefore, the system may collapse. So, to make it statically just the right number to make it statically determinate, I need m members in a truss, with m being equal to 2j minus 3, where j is the number of joints in this. Let us understand how this condition comes about. So, if I take a truss which is externally statically determinate, that means it has 3 constraints from outside. 3 constraints could be in the form of 3 forces, 2 forces, 1 torque, or whatever. So, let us take 3 forces. And then if the number of joints is equal to j, then at each joint if equilibrium condition is applied, then we have number of equations equals 2j, because at each joint, since it is a point, there will be only 2 equations, summation f x equals 0 and summation f y equals 0. And as we saw earlier, with m members, in the truss, there will be m tensile or compressive forces. So, total number of forces is equal to m, which are arising from the members of the truss, plus 3 external forces, and number of equations, equilibrium equations, counting 2 for each joint, is equal to 2j. If I should be able to solve for all the forces, then the number of equations should be equal to the number of unknowns, which gives me 2j minus 3 equals m, and that is the equation for statically determinate trusses if the trusses are externally statically determinate. So, for external statically determinate trusses, 2j minus 3 equals m, and that is how we get this equation. Let us see the structures that I made earlier, whether they satisfy this or not. So, let us see, the first structure that I made was this one and the second one was this one. Let us see that. So, the first structure that I made was like this. Number of joints is equal to 1, 2, 3, 4. So, 2j minus 3 is equal to 8 minus 3, which is equal to 5, and I have precisely 1, 2, 3, 4, 5 members. This is a statically determinate structure. The other structure that I made was like this. The number of joints here is equal to 1, 2, 3, 4, 5, 6, and therefore, 2j minus 3 is equal to 9, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9 members. So, this is also a statically determinate structure. If I add more rods here, maybe like this, maybe like this, although I am increasing the number of joints. So, at some point it may become a system which is statically indeterminate. On the other hand, if I have less members than 9, then it will be a structure which may collapse. It will not transfer forces in an easy manner or a consistent manner to the sides. You notice that both the ends are put on a fixed point. Actually, this makes the system indeterminate because the number of external forces is now 4. We could make it determinate by putting the right hand side of the system on a wheel or on a roller. Let us take one example of this. And this is a very particular structure that I am taking. Let us take 2 rods, and I am making it very carefully, which are have a fixed joint here, fixed joint here, one joint here, and I am loading it right here. This is just to again motivate and play around with forces and things like those in a truss. Now, you see, if I start with this rod, let me call this 1, 2, 3, start with rod 1, 2, put it on a pin joint here and load it. The rod will tend to rotate like this. To stop that, what I do is I put another rod here, so that this is an isosceles triangle, and make a fixed joint on the other side also, and then the load is here. But the moment I do that, you see, if I look at this structure as 1, there is a load W, there will be reaction here, and in this case I know because the symmetry is going to be W by 2. Here also the reaction is going to be W by 2, and if I look at this pin here, from the support, fixed support outside, it is getting a force W by 2 like this, and is being pushed by this rod in this direction. So, the net force on this will be in this direction. It will not be in equilibrium. To bring it to equilibrium, I add another rod here, and that makes a stable truss for me. In this particular situation, where this is an isosceles triangle and I put the load on this joint. Let us analyze this further. So, I have this structure here, and I have already argued that I need these 3 rods to bring it, make it a stable structure. If I look at this system, there is a force W by 2 acting here, and force W acting downwards. What I want to know is what is the forces and in these different rods or members of the system. So, let us call this 1, 2 and 3. Let us look at rod 1 2. If I look at rod 1 2, it is in equilibrium under the forces that are applied on it by this pin here and this pin here, only two forces. And remember what I said in the beginning of the lecture, that if a body is in equilibrium under two forces, those forces are collinear. So, in this case there will be a force on this acting this way and there will be a force acting on it this way at these 2 points. This is the only way these two forces can act, otherwise the body will not be in equilibrium. Similarly, on rod 2 and 3, there are two forces acting due to pin at 2 and pin at 3. Again, the forces have to be collinear. So, the forces have to act in this manner, 2 and 3. And on the rod 1 and 3, again 1 and 3 is in equilibrium, the rod 1 3 is in equilibrium. So, the forces at 1 and 3 have to be collinear, because if a body is in equilibrium under two forces, they have to be collinear. So, now we know the force directions. Let us analyze this further. If all the rods are equal, then all these angles will be 60 degrees. Now, I know that pin 1 is in equilibrium. Pin 1 has a force acting on it, which is W by 2. Since for the rod 1 2, I made forces that are pushing the rod, so the rod would be applying a force the other way on the pin. Similarly, force on 1 3 that I made was also pushing the rod, that is, the force is compressive, the force that will be acting on the pin would be in opposite direction. So, let me call this force 1 3, this is force 1 2, and this pin is in equilibrium under these forces. Since the forces are acting at one particular point, this I do not have to write the torque equation, only thing I will write is that summation f x would be equal to 0 and summation f y would also be equal to 0. This gives me that f 1 2, this is 60 degrees, so would be this. So, f 1 2 sine of 60 degrees is equal to W over 2, and that gives me f 1 2. Similarly, summation f x is equal to 0. I recall that I am talking about this pin. On this pin, there is a force this way, f 1 3, f 1 2 and W by 2. This angle is 60 degrees. I am going to have f 1 2 cosine of 60 degrees plus f 1 3 is equal to 0, or f 1 3 is equal to minus f 1 2 cosine of 60 degrees, which is nothing but minus f 1 2 over 2. F 1 2 on the other hand, we found out is equal to W over 2 sine of 60 degrees, which is nothing but W over root 3, and therefore, f 1 3 is equal to minus W over 2 root 3. I have found the forces on member 1 3, I have found the force on member 1 2. To find the force on the third member, that is F 2 3, I have a choice. Either I can go to this point or this point and consider the equilibrium conditions there. If I go to point 2 here, then according to the way we have made forces, point 2 would be feeling a force this way, which is F 2 3, a force this way which is F 1 2, which we have already determined to be W over root 3, and a force this way which is W. Now, summation f x then gives you that F 2 3 should be equal to F 1 2. Of course, this comes with F 2 3, this angle is 60, cosine of 60 degrees with a minus sign, plus F 1 2 cosine of 60 degrees is equal to 0, and this gives you that F 2 3 equals F 1 2 equals W over root 3. So, we have determined all the forces in the system by looking at equilibrium of each point. One point I would like to make about F 1 3 is that F 1 3 came out to be negative. What that means is that the direction that we had assumed for F 1 3, that is, we had assumed it to be like this, the compressive force is actually not so, it is a tensile force, that is, the rod F 1 3 is being pulled in this manner with force W over 2 root 3. For completeness, I should point out that the triangle that we just made should actually be fixed like this on a fixed pin on the left and on a roller or wheel on the right. This will make the system statically determinate. Through this, what I have done is provided you an example of solving for the forces in a truss through method of joints. That is, we take each joint, each pin at each joint to be in equilibrium. Now, a few subtle points about trusses. If I take these 3 rods and replace them by slightly wider members, with the width of the members being much smaller than their length, and instead of applying a pin joint, bolt them here by a plate. That is, each joint here looks something like this, and I put a plate here with bolts here. Even then, it is a good approximation to take this as a pin joint. So, a good to take a joint as a pin joint. Why? Because the width is very small, and therefore, even if there are little forces that are applied by these bolts, the torque produced would be almost 0, negligible compared to the torques that are applied by external forces, and therefore, it is a good approximation. By the way, the plate that is put here, and you notice it next time when you cross a bridge, is known as the gust plate. So, let us see now, given a basic truss like this which I just solved for, how can I make a bigger truss? Let us see, if I want to extend this further, I would apply, I put a member here and give a joint here. This joint now has 3 members that can provide equilibrium. Then this point Suppose I don't want to provide a support here, I have to provide one more member, and I could provide a fixed support here, a fixed support here. That is one possible truss. Another way is I have this basic truss which is fixed here, fixed here. I don't want to fix it here now. I provide one more member, so that this point now has 3 members that can provide equilibrium to it. This is a fixed point, and suppose I want to put this under a fixed point. Then this member has one force coming from the fixed support, one from this member. So, I have to provide one more member, so that there are 3 forces acting on it. But this gives a loose end here. I could fix this loose end by putting 2 members here. Now, you see each member has a minimum of, each joint has a minimum of 3 members, so that this becomes a statically determinate structure. Let us see if it is. Number of joints in this case is 1, 2, 3, 4, 5. So, j equals 5 implies 2j minus 3 is 7, and 1, 2, 3, 4, 5, 6, 7 members, and therefore, m, which is 7, provides that this is a statically determinate structure. This is capable therefore of remaining in equilibrium when loaded. Several examples of trusses that you see in everyday life are, for example, Pratt Truss, which you see Pratt Truss, which is like this. It is put on the supports here, and these are joints. Let us see the number of joints here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. So, 2j minus 3 is 21. Number of members is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So, this is a statically determinate truss and capable of remaining in equilibrium. These points can be fixed. On the other side, either I can have a fixed pin, or usually you put it on a wheel. I will comment on this a little later. Let us look at some other trusses in the meantime. The other one is Hoe Truss, which is like the Pratt Truss, except that the fixtures are the other way. Again, you can count the number of joints and number of members. They are consistent for it to be a statically determinate truss. Third one is a Warren truss, which is like this. So, these are different variations on the way the members and joints are fixed on a truss, and this side again I put it on a roller, and this side is fixed. Again, j equals 12 and m equals 21. So, they are consistent. J equals 12 and m equals 21. So, they are also consistent for them to be statically determinate trusses. Why we put a wheel here or a roller here is because what we have assumed in all this is that these members are rigid members. However, in reality they deform, and when they deform, the distances may change, and to accommodate for that you put a roller here rather than putting it on a fixed pin joint, so that the stresses are not developed in these members. Notice that even when the wheel is put instead of a fixed joint, the truss is capable of remaining in equilibrium, since there was a redundant constraint on the system to start with. So, the question that we now want to answer is, how do we calculate forces in the members of a truss, and that will be analyzing the trusses. We are going to restrict ourselves to plain trusses, which are the ones that I showed you, and we are going to do our analysis under certain assumptions. Number 1, when these members, which we take to be sort of rods, but are wide enough, when the middle line, wherever it cuts, we are going to take that intersection as a pin joint. So, intersection of the middle line of members of a truss are taken as pin joints, and as a corollary, we are also any plate or bolting that can be done here, we ignore the torques arising because of that. Next, we are going to assume that at any truss, all the load is going to be only on the pin joints. That is the next assumption. And finally, if members, that is these rods, have weight, the weight is equally distributed on the pin joints. That is, if for example, a member may have a weight W, then I am going to say that this pin joint bears W by 2 and this pin joint also bears W by 2 of this weight. So, the weight is equally distributed on the pin joints. Under these assumptions, we analyze the trusses. There are two methods of analyzing the trusses and getting the forces on various members. One is known as the method of joints, and the other one is known as the method of sections. You have already seen a glimpse of gotten a glimpse of method of joints when I analyzed a very simple truss earlier. What is done in method of joints is that each point, each joint of the truss is brought in equilibrium under the applied forces. So, if I have a truss like this, and it is loaded here, then we start with a point where the load is and see how that point is in equilibrium. That gives us the forces in the various members that are connected with that point in terms of the applied load. In case you have more forces than you can solve for in this case, then you first solve for the reactions at the fixed points, and then because there are only two members at those fixed the n fixed points, you can solve for the forces in those members and then go on to the next joint and so on. I am going to demonstrate the method of joints through several examples. As the first example, let me take a system, a simple system which is made of 4 rods with one fixed pin joint here. This is a rod, another rod like this, the pin joint here, third rod like this, and this is on a roller, a fourth rod like this, and there are 2 ropes along the diagonal. Let me call this system A, B, C and D. This length is 4D, this length is 3D, and we load the system once at point B by a load L, and another loading is done at point C, the same L. These are 2 ropes, A, B, C and D, and in both the cases I want to know the forces developed in these rods or members and these ropes. I should also mention here that this problem is taken from the book of Merriam. This is quite a nice problem because it teaches us quite a lot of things in one problem. So, let us first take this particular case where we have, I will just make it a very simple manner, these points. This is on a roller, this is on a fixed pin, this is a rope, this is a rope, this is the load. This is 4D, this is 3D. Now, on the point, this is A, B, C, D. On point D, there will be only a reaction in the horizontal direction. Let me call it ND on the entire system. So, ND in horizontal direction. On point A, there is going to be a reaction in the vertical direction. Let us call it N y, N a y, and horizontal direction N a x. This is if I consider the entire system as a whole. So, on the entire system, if I make a free body diagram, there is a load L, there is a reaction here N d, there is a reaction here in the vertical direction N a y, and there is a reaction here in the horizontal direction N a x. Since there are only 3 external forces N d, N a x and N a y, these can be determined very easily. It is a 2-dimensional problem. So, let me make it again. There is a load L, N d, N a x, N a y, summation f x equals 0 gives N a x plus N d equals 0, and summation f y equals 0 gives N a y equals minus L. Sorry, I should write N a y minus L equals 0 or N a y equals L, that is, it is vertically upward direction. Summation torque about D, this is point D, A, B, C, is equal to 0, gives 4 D times L clockwise plus 3 D times N A x also clockwise should be 0, and this implies that N A x equals minus 4/3 L, and minus sign tells you that its direction, let me make the good direction with red, should be this way. So, this is N A x. And from this equation that N A x plus N D equals 0, N D also comes out to be in the right direction, 4/3 L. So, now we know the forces, external forces in the system. What we have is L here at point C, point A, I have a force acting towards the left, 4 L by 3, force acting towards vertically up L. I have a force acting on this joint in this direction, 4 L by 3, and I want to calculate other forces. This is point C, this is point D. Let us take the joint D or pin at D and see what the forces on D are. Now, we are really using method of joints. Each joint we are going to bring into equilibrium by applied forces. At point D, there is a force in horizontal direction 4 L by 3. There is a force, and now I am anticipating that the force by rod DC is going to be towards the left, F DC. There is a force by the rope. Now, since this is a rope, it can apply only a tensile force. I mean, the rope can exist only under tension, not under compression. So, it will not support a compressive force. So, it can apply only a force in this direction, F, let us call it D B, and there is a vertical force due to rod F A D. Now, one can see that this joint is under a force 4 L by 3. So, this is going to be pushed to the right, and if it is going to be the push to the right, the rope is also going to be pushed in, but rope cannot sustain any compressive force. So, F dB is going to be 0. If F dB is going to be 0, that means there is going to be no vertical component of force due to element dB. This also implies that FAD is equal to 0. So, we have found two forces, FDB, which is 0, and FAD, which is 0. Let us now consider the forces in the horizontal direction. Since FDB is 0, summation Fx equals 0 gives me FDC equals 4 L by 3, and positive sign tells me that I have found the correct direction. Since the rod DC is pushing the point out, the rod DC is under compressive forces. So, this is compressive. Let us move on. So, what we have found in this that at point D, there is a force 4 L by 3 and A, B, C, D, F A D is 0, F D B is 0, F D C is compressive 4 L by 3. Let us now look at point C. Point C is under a force F D C, which is 4 L by 3. There is a force, and I am already anticipating the right direction, F A C, pulling it in. That means AC rope is under tension, and remember again, AC is a rope, so that it can support only tension, no compressive force. And there is going to be a force F B C. This angle is, let us say, theta. This is theta. So that, let me write in different color, cosine of theta is 4/5 and sine of theta is 3/5. So, summation f x equal to 0 on point C gives me f a c cosine of theta equals 4 L by 3. So, f a c is equal to 4 L by 3 divided by cosine theta. So, that is 5 over 4, and this gives me 5 over 3 L. That is the tension tensile force on the rope. Now, similarly, if I do summation f y, so again let me make the picture. A, B, C, D, we have found F A C to be 5/3 the load. This is the load. At point C, this is 5/3 the load, this is 4/3 the load, and this force is F B C. Summation F y equal to 0 gives me F B C equals 5/3 L times sine of theta. Sine of theta we have already calculated is 3/5, and therefore, this comes out to be L. So, F B C is pushing it down, and that means F B C is, the rod is being compressed, so it is compressive. So, we found force F D C, we found force F B C, we found force F A C, we found force F A D, we found force on F B D. The remaining forces are forces only on F A B. Let us now look at point B. The joint B is under load L, then it is being pushed by F B C by L. There is no force, 0 force due to the rope, and therefore, F A B comes out to be 0. Cut. This follows from the condition summation f x equals 0 on B. So, now we have found all forces, and let us see again by checking at point A whether all the forces are consistent. So, what we have found on this frame A, B, C, D, F A B is 0, F AC is 5/3 L, FDC is 4/3 L, FBC is equal to L, FAD is equal to 0 and FDB is equal to 0. With these forces, let us see if point A is under equilibrium. Remember, we found that on A there is a force in this direction which is 4/3 L. There is a force upwards which is L, and now I know, because of the tension in the rope, there is a force FAC which is 5/3 L. This angle is theta. Recall again that cosine of theta is 4/5 and sine of theta is 3/5. If everything has been solved correctly, point A again should be in equilibrium. So, FAC cosine of theta comes out to be 4/5 times 5/3 L, which is 4/3 L, and this force is going to balance this force out. So, horizontal forces are 0 and FAC sin theta comes out to be 3/5 times 5/3 L, which is L, and this force is going to balance out this particular force, and therefore, point A is in equilibrium and we have solved the problem correctly. Cut. कितना टाइम हुआ है? For the second part, where the system is loaded differently, that is, the load is at point C. I will leave this for you to work out. In the next lecture, we will be taking slightly more complicated and bigger examples and see how method of joints helps us in solving the problems for trusses.